Good evening, everyone, and welcome to this ninth interactive session of NPTEL GATE series. Today, we'll be looking at engineering mechanics, focusing on calculus. So, I'm Naresh, a research scholar in the Department of Civil Engineering at IISc. Just get into the session. So, today we'll be looking mainly on problems, mainly problems on this limits, continuity, and differentiability, directional derivatives, some integration, and also ordinary differential equations. So these topics have already been covered by other scholars in the earlier sessions. So I'm not getting much into the theory, but of course I'll be explaining a little bit while solving the problem. But to save time and for at this stage it is more important to have practice. So we'll solve more number of problems. Typically we do 2 problems and a lot of theory. This time we'll have more problems and minimal theory. So let us get started. This question appeared in GATE 2009 civil engineering paper. So this is a problem from directional derivatives. We are given a function f of x comma y comma z. This is the function, and we are asked to find the directional derivative of this function at the specified point p in the direction of a certain vector. So imagine this function to be some scalar field. It can be the temperature in a room or something. And at a given point in the room, we're asked to find the how fast the temperature field varies in a given direction. So for example, if so, suppose this is the domain. For this problem, the domain is not important, but suppose this is where the function f of x comma y comma z is defined, and this point P lies inside this cuboid. And at the point P, they're asking the directional derivative. So basically, what directional derivative is, you take a small vector in the direction. So this is an exaggerated view. Let us call this vector as u. You move from the point P to another point, say P dash, along the direction u. So you slightly move in the direction u along the vector u from the point P and to the point P dash. And you would have traversed some distance. Say that distance is some distance, say call it S. So what is the how is directional derivative defined? So so how much the function f changes from going from point P to P prime divided by the distance moved along this direction. In the limit, the distance going to 0. So you know the concept of usual derivatives. You have a function as a function only of one variable, have x and x plus delta x. The derivative of a function y is equal to f of x at the point x is defined as the limit of the difference y as you go from x to delta x. So this is the difference divided by the infinitesimal value delta x in the limit delta x tending to 0. Same thing. So just that it's not in one direction, one dimension. You have a direction specified, which is u, and you divide it by this. So let us directional derivative in the direction u of a function f is defined as f of, suppose x is the point where you need to find the directional derivative. Just move along u by a small value h minus f of x divided by the distance you have moved. Suppose u is a unit vector, then the distance we have moved is just h. So u is a unit vector, so the magnitude of u is just 1. So the magnitude of hu is, it is just h. In the limit h tends to 0. So this, in our case, we are looking at 3-dimensional problem. So in our case, it is just f of x plus h times the x component of u, y plus h times the y component of u, plus z plus h times the z component of u minus f of x comma y comma z divided by h. So again, limit h tending to 0. Using Taylor series, you can expand the first term. So if f is a differentiable function, if f is differentiable, you can expand the first term in terms of Taylor series. So what do you get? You get uh, you can write it as f of x comma y comma z plus partial f with respect to x. Apply chain rule to take the derivative of this with respect to x into h ux plus partial f with respect to y h uy plus partial f with respect to z h uz plus you have the higher order derivatives in f. So you may have del f square by del x square 1 by 2 h ux the whole square and so on. But all of these are of have the term h square minus f of x comma y comma z, the entire thing divided by h. Again, in the limit h going to 0. So you can easily see that the first term cancels with this, and from these terms h gets cancelled. So we have a h in the denominator, and these all terms you can take h square commonly out. Therefore, when you set the limit, you can cancel one h in the numerator with the h in the denominator. So there's a h multiplying with all the higher order terms, and in the limit h tending to 0, these terms vanish. Therefore, the directional derivative of the function with respect to uh, in the direction u at a given point x is nothing but partial derivative of f with respect to x. There's a h which gets cancelled into x component of u plus partial derivative of f with respect to y component of u plus partial derivative of f with respect to z into z component of u. This you can write in a concise form as the gradient of f dot product with the vector u. The important thing to note here is that this is true only if u is a unit vector. So so the directional derivative is dependent only on the direction, not on the magnitude of the vector which is specified. So let us take u as in our case, what is f? In our case, f is x square plus 3y square plus 2z square. Let us find out grad f. So partial f with respect to x is nothing but 2x. Partial f with respect to y is nothing but 6y. And partial derivative of f with respect to z is 4z. And the unit vector u, the given vector u is I minus j plus 2k. That is plus 2k. But we want the unit vector, so divide it by the norm. So the norm of this is 1 square plus minus 1 the whole square plus 2 the whole square. So the denominator is 1 by root 6. Therefore, the vector u is in the component form, it is 1 by square root of 6 minus 1 by square root of 6, 2 by square root of 6. Now we can apply the formula directly. So the directional derivative of this function in the direction u is nothing but 2x by root 6 minus 6y by root 6 plus 4z by root 6. We are asked to find out the directional derivative at the point where x equal to uh, x equal to 1, y equal to 2, and z equal to minus 1. So x equal to 1, y equal to 2, and z equal to minus 1. Substitute that into this, we get 2 into 1 minus 6 into 2 plus 4 into minus 1 by square root of 6. So if you evaluate what this comes out to be minus 18 by root 6. What is minus 18 by root 6? Nothing but 3 into 6 by root 6, which is minus 3 square root of 6. So the correct answer is option B. So the correct answer is option B, minus 3 square root of 6. Let us go to the next question. What should be the value of lambda such that the function defined below is continuous at x equal to pi by 2? So this is a problem, of course, in limits, continuity, and differentiability. So this deals with continuity. And what we have is a function in one variable. It's a 1D function. And how is continuity defined in 1D function? So a function is said to be continuous if a function f of x is said to be continuous at a point x if f of x, the function value at x is equal to the limit of the function. Say, let us take this point as x naught, f of x naught, the limit of the function as x tending to x naught. So for this equality to make sense, the limit on the right hand side should exist, which also means that, of course, this means that limit extends to x naught, f of x exists. And in the case, existence is very simple. It is just that the function has the left hand limit has to be equal to the right hand limit. Given this definition, let us examine the continuity of the given function. We are given f of x is equal to lambda cos x by pi by 2 minus x. If x is not equal to pi by 2, and it is equal to 1 if x is equal to pi by 2. So f of pi by 2 is 1, and f of x, if x is not equal to pi by 2, then it is the above function. Now for this function to be continuous, the limit x tending to pi by 2, f of x should be equal to f of pi by 2. But the limit f of x as x tends to pi by 2 should be evaluated using this, because when x is not equal to pi by 2, it is approaching pi by 2 either from the left hand side or the right hand side. The function is defined as this. Therefore, limit x tends to pi by 2, lambda cos x divided by pi by 2 minus x is equal to, what is f of pi by 2? It is 1. So let us simplify this further. You can write cos x as sine of pi by 2 minus x. Therefore, limit x tends to pi by 2, lambda sine pi by 2 minus x divided by pi by 2 minus x is equal to 1. So this is the condition we have. Lambda is independent of x, so that can be taken out of the limit. So you can write this as lambda times limit x tending to pi by 2 sine of pi by 2 minus x divided by pi by 2 minus x is equal to 1. Now you can make the change of variables. Substitute y is equal to pi by 2 minus x. So if x tends to pi by 2, then y tends to 0. So this limit can be rewritten as lambda limit y tends to 0 sine of, in place of pi by 2 minus x, you can substitute y is equal to 1. We know that this limit, if you evaluate using the L'Hopital rule, this limit is nothing but 1. Therefore, lambda multiplied by 1 is equal to 1. Lambda is equal to 1. So the correct answer for this question is option C. Let us go to the next question. So this is a problem in integration, definite integrals. What is the value of the definite integral, integral 0 to a square root of x by square root of x plus square root of a minus x? The problem seems very difficult at the outset because of the square roots involved, but it is actually simple. This particular problem with the definite integral is actually simple. It is not difficult. But if you make this an indefinite integral problem, or if we change the limits to something else, then this problem is really difficult. So there is a trick involved in solving the problem. Let us see what it is. So that makes use of the symmetry of the integrand with respect to x and a minus x. So let us see what it is. Let us call the integral as I. Let us suppose if we do the integration and substitute the limits, suppose we get the value I for this definite integral. So let I is equal to integral from 0 to a square root of x divided by square root of x plus square root of a minus x dx. Now let us make a change of variables. Let us call this equation 1. So let this given expression be equation 1. Let us make a change of variables that let t is equal to a minus x, which means x is equal to a minus t and dx is equal to minus dt. So everywhere in this given expression, we substitute x is equal to a minus t. So when x is equal to 0, t is equal to a minus x, a. So when x is equal to a, t is equal to 0. Therefore, the integral, the definite integral will transform as, so I goes from t going from a to 0. When x is 0, t is a, and when x is a, t is 0. And what do we have in numerator? It is x. So in place of x, substitute a minus t. And denominator, we have an x. So that becomes a minus t plus square root of a minus x. A minus x is nothing but t. And the differential dx transforms to minus dt. So simplify this further, take the minus sign out. So you get minus integral going from a to 0, square root of a minus t divided by square root of t plus square root of a minus t dt. Bring the minus sign into the integral limits, so I can switch the lower and upper limit. So this becomes integral 0 to a square root of a minus t divided by square root of t plus square root of a minus t dt. Note that we are integrating with respect to t. So t doesn't appear in the final expression. So t is just a dummy variable. So I can replace t with x. Replace t with x. So we get I is equal to integral 0 to a square root of a minus x divided by square root of x plus square root of a minus x dx. Let us call this equation 2. Now compare 1 and 2. If you see 1, this is what we have, square root of x by square root of x plus square root of a minus x dx. The limits are the same, the integral variable is the same, and the integrand is something, and the integral itself is I. And in 2, what do we have? It is the same integral I is also equal to integral 0 to a, the limits are the same, the integrating variable is the same, but the integrand is slightly different. So add 1 and 2. So by now you can see why we are adding 1 and 2. If you add 1 and 2, you get the denominator of the integrand is also the same. So you can directly add the numerators. So what we get is, so the left hand side, if you add the left hand side, you get 2 times I is equal to, the limits are the same. So you can take it commonly out, integral 0 to a. And from the first integral, we have a square root of x. From the second integral, we have a square root of a minus x. The denominators of the integrands are the same, which is square root of x plus square root of a minus x. The integrating variable is the same, which is dx. So this is nothing but 1. So these two cancel each other. So you get integral 0 to a dx, which is nothing but a. So 2 times the integral is 0 to 2 times the integral is a. Therefore, the integral itself is a by 2. So as I said, this problem is very simple just because the integral itself is from 0 to a. If we change the limits of the integration, or if it becomes a problem in indefinite integrals, then it is very difficult to solve this problem. So the correct answer to this problem is a by 2, which is option B. Let us go to the next problem. So this is a very simple problem in vector analysis. A and B are two arbitrary vectors with magnitudes A and B respectively. Then we are asked to find out the magnitude, the square of the magnitude of the cross product of A and B. So we know that the cross product is defined as if you have two vectors A and B. The cross product is the vector which is perpendicular to both A and B with a magnitude equal to the area of the parallelogram enclosed by A and B. So you translate A to the head of B to get another vector A. So vectors can be translated without changing their magnitude and direction. Similarly, we translate B to the head of A. This encloses a parallelogram. The magnitude of A cross B is nothing but the area of parallelogram enclosed by A and B. And what is that? The area of this parallelogram is base into height, which is base into height. If the angle between these two is theta, the base of the parallelogram is, we have A, the magnitude is A, and height of the parallelogram is B sine theta. And what is the direction of A cross B? It is perpendicular to both A and B. It's perpendicular to the plane containing A and B. So that is not important in this problem. We are interested only in the magnitude. So what is A cross B the whole square? It is nothing but A square, B square, cos square theta. Sorry, sin square theta. Let us simplify this further. We can write sin square theta as 1 minus cos square theta, which means A cross B the whole square is nothing but A square B square into 1 minus cos square theta, which is nothing but A square B square minus A square B square cos square theta. Let us call this equation 1. Now let us look at this part, A square B square cos square theta. We can write this as AB cos theta the whole square. What is AB cos theta? AB cos theta is nothing but, so we have a vector A and you have a vector b enclosing an angle theta. AB cos theta is nothing but A dot B. The dot product between A and B is defined as AB cos of the angle between A and B. So this is nothing but A dot B the whole square. Now substitute this into equation 1. Therefore, we get A cross B the whole square is equal to A square B square minus A dot B the whole square. So this is the correct answer. And this is option A. A cross B the whole square is equal to A square B square minus A dot B the whole square. Let us go to the next question. So this is a problem. This appeared in GATE 2011. It's a problem in ordinary differential equations. We are given a linear differential equation. So what we are given is a linear ordinary differential equation. Uh, yeah, linear ordinary differential equation with some initial conditions. So it's an initial value problem. So the equation is dy by dx plus y by x is equal to x. So this is not in a variable separable form. So we can say it is not variable separable. Why? You just separate dy and dx. See what you get? We get dy plus y by x dx is equal to x dx. So you cannot write it as one part which depends only on y and another part which depends only on x. So we get dy plus y by x minus x dx is equal to 0. This is what we need to solve for. And this is not in a variable separable form. We can't integrate it directly. So we look for integration factors. So we look for integration factors. What are they? So this is of the form m dx plus n dy is equal to 0. So this is of the form m dx plus n dy equal to 0. If m is some partial u with respect to x and n is some partial u with respect to y, then what we have is partial u with respect to x dx plus partial u with respect to y dy is equal to 0. Right? If this is the case, then the solution is direct. It is just u of x comma y. So if that is the case, this is nothing but the differential, the total differential of u with u, right? This is the total differential of u. So basically, it means du is equal to 0, which also means that u of x comma y is a constant. So this is basically the solution. This is an implicit form of the solution x comma y. But now what we have is not that. We need to look. So when can we say that m is some derivative of u and n is some derivative, some partial y with respect to u? So we know that the mixed derivatives are equal. But what is x derivative of this? This is nothing but dou by dou x of n. And this is nothing but dou by dou y of n. So these conditions are satisfied. then it is an exact differential. So in our case, what is n? N is what is multiplying with dy, so n is 1, and m is y by x minus x. So we can clearly see that del n by del x is equal to 0, and del n by del y is equal to 1 by x. So clearly, del m by del y is not equal to rho n by rho x. Therefore, it is not an exact differential. It is not an exact differential. So how we solve the problem is we look for integrating factors. Look for an f of x multiplying with both sides such that f m dx plus f n dy is an exact differential. So in general, f can be a function of x and y. So actually, it's f of x comma y. This should be an exact differential. But let us assume that f is a function only of x. And in our case, we multiply throughout by f. So we get f dy plus f into y by x minus x dx should be equal to 0. This is what we have. And if this should be an exact differential, what is the condition? Dou f by dou x is equal to dou by dou y of f y by x minus x. So let us see what it is. We have f as a function only of x. So this is nothing but f dash of x is equal to. So f is a function only of x, and this is only y. So this becomes f of x divided by x. The second term vanishes. This is a function only of x. F of x times x is a function only of x. So its partial derivative with respect to y vanishes. Let us solve this small ODE. This is a very simple ODE. So this is variable separable. How? You can write it as df by dx is equal to f by x, which means df by f is equal to dx by x. If you integrate on both sides, you get log of f is equal to log of x. So which means f is some plus some constant, say log of c1. So f is just some constant times x. Now multiply the above equation by f. So we have determined what f will make it an exact differential. So multiply this by a constant times x. So if you do that, we get a constant times x dy plus the constant times x multiplied y by x minus x dx is equal to 0. So the constant we can take it to be not equal to 0 and take it to the other side. So we get x dy plus x, y minus x square dx is equal to 0. So what does this mean? You can suppose there is a function u, its y derivative is x, and its x derivative is y minus x square. Now integrate these separately. So u of x comma y is integrate this, you get xy plus some function of x only because the integration is with respect to y. And in this case, you get u as a function of x and y is xy minus x cubed by 3 plus some function of y only. Equate these two. xy is the same. So we have these two. Equating the two, we get xy minus x cubed by 3 plus f of y, which means g of x is minus x cubed by 3 plus f of y. Note this is a function only of x, but this is a function both of x and y. Therefore, f of y should be a constant k. So g of x is nothing but minus x cubed by 3 plus k. So what is u of x comma y? U of x comma y is xy minus x cubed by 3 plus k. But what is the solution that we get? The solution is u of x comma we get du of x comma y is equal to 0, which means u of x comma y should be a constant. So set this xy minus x cubed by 3 plus k is equal to some constant. So this k can get into this. So you get xy minus x cubed by 3 is equal to some constant. What is given? They are given that when x equal to 1, y is also equal to 1. So let us evaluate what this constant is. We get 1 minus 1 by 3 is equal to c. So the constant c is nothing but 2 by 3. But what we actually want is y as a function of x. Therefore, rearrange this equation, divide throughout by x, we get y minus x squared by 3 is equal to c, which is 2 by 3 x. Therefore, y is equal to 2 by 3x plus x squared by 3. So this is our solution. This is the solution to our differential equation. And this is option 2 by 3x plus x squared by option D. Now let's go to the next problem. It's given for an analytic function f of x plus iy is equal to u of x comma y plus iv of x comma y. U is given by this. The expression for v considering k to be a constant is. So this is a problem in complex variables and also calculus. We are given that the function is analytic. So if a function is analytic, it admits a Taylor series representation about the point x comma y. So given that the function is analytic, therefore f of x comma f of x plus iy can be expressed as, so let z is equal to z equal to x plus iy. And if it is analytic, you can express f of uh, x plus delta x plus I y plus delta y as del f by del x dx. So if you move slightly from the point x comma y, so let z equal to x plus iy, let z plus delta z be x plus delta x plus I y plus delta y. So in the complex plane, you're given a point x comma y, and you know that the function is analytic at that point. And if it is analytic at that point, it means that you can express the function as a Taylor series expansion about that point. So you consider another point z plus delta z in the small neighborhood of z. So this arrow is small arrow is delta z, and this is z. And delta z can be in any direction. So f of x plus delta x plus I times y plus delta y is nothing but. So now you can use the real variable Taylor series. So this can be treated as a function of two variables x and y. So this will be nothing but f of x plus iy plus partial f with respect to x delta x plus uh, partial f with respect to so we get so this is the real part of it x plus delta x plus partial f with respect to y. Sorry. So this is nothing but u of x plus delta x comma y plus delta y plus I v of x plus delta x y plus delta y. Now these two are two real functions of two real variables. So this you can write it as u of x comma y plus partial u with respect to x delta x plus partial u with respect to I delta y plus the higher order terms plus I times v of x comma y plus partial v with respect to x delta x plus partial v with respect to y delta y plus the higher order terms. And this u plus iv can be taken commonly out so that you get f of x plus delta x plus I y plus delta y minus u of x comma y plus I v of x comma y is equal to what do we have on the right hand side? We have this partial u with respect to x plus partial u with respect to y plus the higher order terms. Here we have a delta x, delta y plus the higher order terms plus I times partial v with respect to x, delta x and partial v with respect to y, delta y and the higher order terms. And u plus iv is nothing but f of x comma f of x plus iy. So this is nothing but and x plus iy can be taken as z. So this is f of z plus delta z minus f of z is nothing but partial u with respect to x delta x plus partial u with respect to y delta y plus so on plus I times partial v with respect to x delta x plus partial v with respect to y delta y and so on. Now divide both the sides by delta z and take the limit delta z tending to 0. So we get so this becomes f dash of z. So we divide by delta z and let delta z tending to 0. So we get it is limit delta z tends to 0 partial u with respect to partial x delta x by delta z plus partial u with respect to y, delta y by delta z plus the higher order terms plus I times partial v with respect to x, delta x by delta z plus partial v with respect to y, delta y by delta z plus the higher order terms. Now this holds for arbitrary, arbitrary delta z. So you can choose in first case, choose delta z equal to just delta x, which means delta y is equal to 0. In that case, f dash of z becomes partial u with respect to x, this term vanishes, plus I times partial v with respect to x. It becomes del u by del x plus I del v by del x. The second case, choose delta z as I times partial delta y, and delta x is 0. So f dash of z becomes, let us call this equation 1. So the first term doesn't contribute. The second term is del u del y times I. So delta z is I times delta y, so that's a minus sign here. Plus the first term doesn't contribute. You get I divided by another I. So it becomes, so del z is I times delta y. So I get an I in the denominator. This I and this I get cancelled. So it is del v by del y. Plus del v by del y. Note that the left-hand sides of equation 1 and 2 are exactly the same. Therefore, these two are equal complex numbers, which means their real and imaginary parts have to be equal. Therefore, the real part of equating the real parts, you get del u by del x is equal to del v by del y, and equating the imaginary parts, you get del v by del x is equal to minus del u by del y. So this pair of equations are called the Cauchy-Riemann equations. You might be already knowing them. These are called the Cauchy-Riemann equations. So if a function f given as u plus iv is said to be analytic or holomorphic, then the real and imaginary parts of the function must obey these pair of this pair of equations. So we are given that f of x plus iy is analytic, and u is given as 3x square minus 3y square. So u is 3x square minus 3y square. Let us find out what del v by del y is. So the partial v with respect to y is nothing but partial u with respect to x. So it is nothing but 6x. So partial v with respect to y is 6x. So integrate once, you get v of x comma y is 6xy. The integration is with respect to y. So you have some function g of x. And we know that partial v with respect to x is minus partial u with respect to y, which is minus minus of minus 6y, which is 6y. And this means that partial v with respect to x is 6y, and integrate once with respect to x, we get v of x comma y is 6xy plus the integration is with respect to x, so the integration constant can be a function of y. Equating these two, so note that the left hand side is v of x comma y in both the cases. We get 6xy plus g of x is equal to 6xy plus h of y. These two gets cancelled. We get a function only of x to be equal to a function only of y, which means both of them are constants. V of x is equal to h of y is equal to some constant k. Therefore, v of x comma y is nothing but 6xy plus a real constant A. So this is the answer, and correct answer to this question is option D. So let us come to the last problem for today's session. The solution of the differential equation 3y dy by dx plus 2x equal to 0 represents a family of what? There are four conic sections: ellipses, circles, parabolas, and hyperbolas. So this is a problem, of course, in partial differential equations. Sorry, it's a problem in ordinary differential equations. Now, looking at this equation, is it a linear or a non-linear equation? Can you make a quick guess? So this is an ODE, but it is a non-linear ordinary partial differential equation. It's a non-linear ODE. Why is it non-linear? Because you have this term, which is a product of the unknown and the derivative of an unknown. So you cannot explicitly write it as y is some that is, you cannot write it in this form, dy by dx as a function of uh, x, y, and so on. So this is a non-linear ODE because it involves the unknown function y and also its product with its derivative. But that doesn't mean it is not solvable. Sorry, it's not that you cannot directly get y as a function of x, but you can do something else. So it is given that 3y dy by dx plus 2x is equal to 0. Although it is non-linear, it is variable separable. That's a good thing. So it is variable separable, but it is non-linear. So things like superposing solutions to get the general solution, that doesn't work. But you can get a general solution. You can get a solution. So it's variable separable. So multiply by dx rho, you get 3y dy plus 2x dx is equal to 0. And note that this is an exact differential. So is it an exact differential? That is, so let m, what is multiplying x? It is 2x. So dx is multiplied by 2x. So m equal to 2x, n equal to 3y. And we have an equation of the form m dx plus n dy equal to 0. It is said to be an exact differential if m can be expressed as the partial derivative with respect to x of some function, and n is the partial derivative of some function with respect to y. And in this case, the mixed derivatives have to be equal. This have to be equal, which means the partial y derivative of m and the x derivative of n should be equal. Can we verify that? Yes. In this case, the y derivative of m is 0 and the x derivative of m is also 0. So this is an exact differential. So you have a function whose x derivative is 2x and whose y derivative is 3y. So this can be directly integrated. So you get u of x comma y is x squared plus, so this is direct, plus the integration with respect to y. So I have a function g of y. Again, here you can integrate it directly. So you get u of x comma y is 3y squared by 2 plus the integration is with respect to y. So you have some h of x. So left hand sides are equal. Both of them are u of x comma y. So equating the two, you get x squared plus g of x, g of y is equal to 3y squared by 2 plus h of uh, x. So you get x squared plus x squared minus h of x is equal to 3y squared by 2 minus g of y. What does this mean? The left hand side is a function only of x, The right hand side is a function only of y. So both of them should be equal to a constant k. Therefore, h of x is nothing but some constant x square minus k, whereas g of y is nothing but 3y squared by 2 minus k. Now you can write u of x comma y, reconstruct u of x comma y. What it is? What it is? It is either x square plus g of y or 3y square by 2 plus h of x. Can substitute in any one of the equations. It is let us take the first one. So it is x square plus g of y, which is 3y square by 2 minus k. Or even in the second case, you can take it as 3y square by 2 plus h of x, which is plus x square minus k. Note that both are equal because that is what we enforced. So we have found a function whose exact differential is the left hand side of our differential equation. So we have a function u whose first differential is 0. So m dx plus n dy is equal to 0 is what we have, but m is dou u by dou x, n is dou u by dou y. So we have dou u by dou x dx plus dou u by dou y dy equal to 0, and this is nothing but du equal to 0. What does this mean? This just means that u of x comma y is equal to a constant c. So in our case, u we found it as 3y square by 2 plus x square plus some constant k is equal to c. So this is an arbitrary constant. This is another arbitrary constant. You can mix them. You can combine them. So you get x square plus y square by 2 by 3 is equal to some constant, say c1, and you bring the c1 to the left hand side. You get x square by, let me write it as square root of c1 the whole square plus y square by 2 square root of c1 by 3. Sorry. Square root of 2c1 by 3 the whole square is equal to 1. So this is of the form x square by a square plus y square by b square equal to 1. So it's an ellipse with major axis, with one of the axis root c1 and the other axis root of, and the minor axis root of 2 by 3 c1. So this is an equation of an ellipse. So the correct answer to this question is option A. The solution of the differential equation represents a family of ellipses with only c variable. That brings us to the end of today's session. Thank you for attending. If you have any questions, as I always say, you can post it in the Google group. You can post it in the Google group, groups. Yeah, you can post it here or in the YouTube comment, or you can also bring it up in the next session. So thank you for attending. Let me, I don't see any questions, so let me end the session here.